Evening, everyone. My name is Aditya Sharma, and this is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati under the NPTEL program. And we are into week 9 of this course. And related to week 9's content, we are conducting this tutorial session for your assignments. Instructor for the course is Professor Vinayak Kulkarni from Department of Mechanical Engineering again, and I'm a research scholar here at IIT Guwahati only, Department of Mechanical Engineering. So today's topic is centrifugal compressor. 3 lectures are there in this week's content. So we shall wait for another couple of minutes. After that, we can start today's session. Okay, so we can start with today's session. So centrifugal compressors. Centrifugal compressor is one the type of compressors. The other one is your axial compressor. So we have studied so far that in your gas turbine engines, you have inlet, then you have compressor, then you have combustion chamber, you have turbine, then you have nozzle. And in some cases, between turbine and nozzle, you have afterburner. Okay, so now we are taking this part, right? Compressors to compress our working fluid, the air that is coming inside the engine. Right? So in that effort, we are studying centrifugal compressor. So as the name suggests, by centrifugal force, you are trying to compress air. Okay. So three lectures are there. In lecture number 26 lecture, you have velocity diagrams and the work done expression in case of centrifugal compressors. Then in lecture number 27, you have thermodynamic analysis, stage efficiency, and what is the degree of reaction of centrifugal compressor. Then lecture 28 is about examples of centrifugal compressor. So this we will not take because it has numericals only. And then we will first have one lecture, then its topics, its question. Then next lecture, its topics and question. This way, two lectures we have today. Today's question. Great. So I have one picture of centrifugal compressor also from the front of the centrifugal compressor. This picture is from the front of a centrifugal compressor. So its parts we will see. First is what is the advantage of a centrifugal compressor. So a couple of advantages have been enumerated. Okay. The major advantage is that it provides better protection from the foreign objects. Okay. And its pressure ratio, right? Stage pressure for a single stage that it provides is quite high. That is of the order of 4:1, right? Okay. Then also it is used for low volume rates, low flow rates. So it can handle low flow rates. And if you want to have high flow rates, in that case, you will have to switch to axial compressors. Okay. So this then okay, velocity then comes velocity diagrams. Before going to velocity diagrams. I'll just draw a few things. First, we'll discuss this picture. Okay. So this you see, this part, if you see. Okay. So this is your guide vanes, inlet guide vanes that guide your air that is coming. So if the flow is perpendicular to my screen, okay, that is the axial direction basically. The direction that is perpendicular to my screen, that is basically axial direction of the flow. Okay. And here what I have pointed out is the guiding vanes. So these guiding vanes can open, all right, and these can decide the amount of air that we want inside the compressor. Okay. And this part is your impeller. Okay, which basically is giving this pressure, centrifuging the air. Okay, this is your impeller. Then comes your diffusers that further increase the pressure of your air. Okay. We're diffusing the air that is coming from your impellers. This air is diffused and further the pressure increases. Okay. Then, so I'll draw the enthalpy entropy diagram for it. Also, it is strongly recommended that you go through this animation. All right. So I've given the link of this video, YouTube video. So you can watch this video. You can note down the link to this particular session and then watch this video. So here it has been shown how the flow moves in a centrifugal compressor. So this will give you a good visualization of the centrifugal compressor and how it works. Okay, so I'll draw HS diagram. HS diagram. This is for your guiding beams. So this is from your guiding vanes and your nozzle. Accelerating nozzle plus guide vanes. Inlet guide vanes, in short, we write it as IGV. Then this is for your impeller. Okay. That is increasing your enthalpy. Then your enthalpy again increases at your diffuser. Okay. So diffuser, these are the diffusers I have shown. These are the diffusers. So this is the front image. So this is the HS diagram for your centrifugal compressor. Any doubt you have, you can just write down in the comment section. Then we'll come to velocity diagrams. I'll just discuss the velocity diagram. After that, I'll just quickly write down the expressions for some of the terms that I have. Then we'll move on to questions. Yes. So if we can visualize flow properly inside the centrifugal compressor, then it becomes very easy to draw the velocity diagrams. Okay. So now I'll draw an impeller. From the front, your impeller will look something like this. Okay. This is your center. Okay. Now add the inlet. Now add the inlet. What will happen? How the velocity diagram looks like. Just draw this. So C is for your absolute velocity. V is for your relative velocity. Okay. U is for your velocity of this your compressor. Okay. This rotational velocity. Then this hole is U1. Now if you split C1, okay, it will have one component that is axial in direction, right? One component that is tangential in direction. Now you can, sorry, Now you can imagine what is your axial direction and what is your tangential direction, okay? And how the flow enters inside the centrifugal compressor. If you see this figure number 1, okay? Then now if your this whirl velocity or tangential velocity, if it is 0, okay? If Cw1 is equal to 0, then how will your this diagram become? This will become something like this. Okay. C1 equals to C1, something like this. This will be 90 degrees, right? This is basically fluid angle. This is fluid angle, beta 1. Alpha 1 in this case will be 90. And this is the case for Cw1 not equal to 0. Okay. Right? Then this about inlet. Now about outlet. Now the outlet of your fluid will be in radial direction. Now you please imagine what is radial direction, right? Perpendicular to your shaft. If this is shaft, then it will be in this direction. Okay? Radial from radius. So if your blades at the exit of impeller are radial in direction, in that case, your this beta 2 will be 90 degrees. Okay. This will be C2, and your relative velocity will be equal to your radial velocity, and this is your U2. So also in this case, your axial velocity will be 0. For the radial blades, in axial direction, there will be no fluid flow. I hope you are able to imagine this. Radial basically is this direction, this direction. This. In the screen only. On the screen only, the direction perpendicular to your hub or your shaft. So this is about your inlet, then your outlet. Okay. Then there is forward and backward lanes. So the vanes of your impeller, okay, that centrifuges the air. So this impeller, if you see the figure, the impeller, and you please watch the video also, then you'll again be able to better visualize what is how a guide vane looks like, how it moves, how an impeller looks like, how the arrangement of diffusers is there in the centrifugal compressor. Okay. So the vanes of this impeller, they can either be forward vanes or backward vanes. Now, what is the difference between a forward vane and backward vane? The repercussions of these two arrangements we can see from the velocity diagrams. You can try to understand. Okay. So first I'll draw a backward vane. Okay. So forward and backward vanes. So I'll just draw the backward vane first and the velocity diagram related to it. Then I'll draw your forward. It is something like this. This is the movement of your impeller. Then at inlet, you have this velocity diagram. Okay. So what does this velocity diagram shows is that if you see the discussion of the guide vanes, okay, sorry, this is not about that, but okay. So at inlet, you have this. One component is in, so the absolute velocity that you have, it's one component is in radial direction and one component is in tangential direction. Okay. Okay. Then this is your blade angle, this is your fluid angle. Then at the outlet, what happens is from here we can differentiate what is the difference between these two types of vanes. So this is your absolute, this is your relative, V2 is relative. And if you split your C2, this basically is W2, then beta 2 and alpha 2. So here, if you see, beta 2 is less than 90 degrees. So if your beta 2 is less than 90 degrees, in that case, what is it? It's a backward type of way. Backward way have been used in the impeller. Right? Now, second arrangement is this one. Here the waves are this way. If you see this, u is this, relative velocity is this, and absolute velocity is this. Okay. This is your V2, this is your C2, and this is your U2. Now here beta 2 you see, inlet, let's say, remains the same. V1, 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 and CW2, CW1. So here your beta 2 is greater than 90 degrees, and then this is your forward range. Now, what are the implications of these two arrangements? So we'll first discuss our work done. Okay. So we'll have expression for your our work done. After that, we'll see what are the implications of this. We have to define psi, then flow coefficient, then we'll see what are the implications of these two elements. Okay. All right. Then you see work done, and what is loading coefficient or pressure coefficient, and what is slip. So expression for work done. So in the previous week's content, we have seen what is the expression for work done. So this is this. The CW2 and CW1 basically are the tangential velocity or the whirl velocities. Okay. So So one expression for your work done is, so I'll just directly write down. You can watch lecture number 26 for this. So WC is U2 square 1 minus R2 by U2 cot beta 2. You know what is beta? Okay. Grade angle, CR2 radial velocity, U2 you know what is. Okay. Now here we define flow coefficient, that is 5, and which is equal to CR2 by U2. This is your flow coefficient. So with respect to your U2, how much radial velocity you get, okay, in your fluid that is exiting the impeller. This basically this flow coefficient is. Okay, so your WC becomes in that case U2 square 1 minus 5 cot beta 2. Okay. First is this. Then is your pressure coefficient, or loading coefficient, and we denote it with psi. So this basically is psi is equal to WC by U2 square. Now what is U2 square? U2 square is basically the maximum work that you can take out of this centrifugal compressor. If you have this U2 velocity with you. Okay. So in that case, this basically is the case. If you see this expression, okay, here if beta 2 is 90 degrees, in that case cot beta 2 is cot 90 degree is 0, and you get U2 square. And beta 2 equals to 90 degrees for your radial veins, okay, at the exit of the impeller. Right. So if we work this out, this comes out to be 1 minus 5 to cot beta 2. So now this is expression between your psi and phi. And then we have discussed these forward and backward veins. So now we can draw this relation between these two. So it is like this. So it is something like this. So for your backward veins, the behavior is this for your backward veins. This is your forward veins. This is your radial veins. So your flow coefficient, your pressure coefficient remains constant. Okay. And with your forward veins, it increases. With your flow coefficient, your pressure coefficient increases. So this basically is the repercussion of using these two types of veins. Then there is one more term that is slip factor. Okay. Slip factor is basically the ratio of this. Slip factor is denoted by sigma, and this is tangential velocity to this. So with respect to your U2, how much tangential velocity your fluid has gained, that is your slip factor. Okay. And if we include slip factor in the work expression, then this becomes like this. So this is the expression that becomes. And if we have, in case of radial means, this comes out to be U2 square. We have seen why, because beta 2 becomes 90 degrees. Yeah. Okay. All right. So this is about your lecture number 26. In that case, we can move on to questions. First question here is this. For a centrifugal compressor, the enthalpy of fluid decreases when it flows through. So if you see a compressor in it, basically the enthalpy increases. Okay. If you're compressing air, so enthalpy will increase. But for some part, this enthalpy falls. So out of these four options, which is the correct option? Whether this is nozzle with guide vanes, whether this is diffuser, impeller, or no option out of these four is correct. So we can go to the HS diagram. Okay. Here, if you see, for your accelerating nozzle and your guide vanes, your enthalpy reduces. We are accelerating flow through a nozzle, and also we are using guide vanes to guide the flow into the centrifugal compressor. So So out of the four options, the option comes out to be the correct option. So for your accelerating nozzle with your inlet guide vanes, your enthalpy of the fluid decreases. Okay. Then moving on to next question. It says that in case of your centrifugal compressor, stagnation temperature remains constant from inlet to outlet for dash. So out of the four options, which one is correct? First option is again accelerating nozzle with inlet guide vanes. Then second option is your whether this is impeller. Third is whether this is diffuser or you cannot comment. So again, we will see the HS diagram. Here, if you see the second and third stage, so from second to third is for your diffuser. Okay. And for this part, your this stagnation temperature or total temperature doesn't change. Okay. There is no temperature energy loss. Okay. And then basically you are decelerating your flow and increasing the pressure. But then this will have no effect on your temperature. Okay. So the stagnation temperature remains constant from inlet to outlet for your diffuser. C is the correct answer to this question. Okay. Then moving on to the next question. So centrifugal compressor, question 3 talks about your centrifugal compressor with forward vanes. So it says that centrifugal compressor with forward vanes leads to outlet blade angle of the impeller, which is, so what happens to the blade angle at the exit of impeller or the outlet of the impeller, which is beta 2. So forward vanes, you see, these are your forward vanes. Okay, the right side one. So here beta 2 is greater than 90 degrees. Okay, so in that case, if you see the options, beta 2 is greater than 90 degrees. So third option, C option comes out to be the correct. I hope this is clear. Then moving on to next question. So question number four says that as per the TS diagram for a centrifugal compressor, which of the following options is correct for an accelerating nozzle section? Out of the four options, which one is correct? Please try to answer this through the HS diagram or TS diagram. So static temperature decreases and entropy increases. Static temperature and entropy remain constant. Static temperature increases and entropy decreases. This is opposite of A option. Then fourth option is static temperature and entropy both decrease. Then again, the diagram. So for your accelerating nozzle, what happens is your enthalpy is reducing and your entropy is increasing. Okay, which essentially means your this static temperature decreases and your entropy increases. So I hope this is clear. So A comes out to be the correct answer in this case. Right. Then moving on to next slide. So we have now content of lecture number 27. So before starting this, we'll take a short break, and after that, we will continue with our remaining session. Thank you. Okay, so we can continue with our session. Lecture number 27 we have with us. So here we have friction loss, pressure rise, stage efficiency, then degree of reaction. Then because we will have losses, in that case, we will need, let's say this is this, with your slip factor, considering your slip factor, okay, we have this. But then because you will have windage losses or because of friction, you'll have losses. So you'll need more power than which your numbers tell. Okay. So to include that factor, we introduce this, which is power input factor. And its value is between 2 1.0. So this is your power input factor. Then from here, what has been done is you have got the temperature change across your compressor. That is T03 minus T01 you have calculated. Okay. So this comes out delta T naught for stage comes out is power input factor sigma divided by PP U2 square. Okay. This is for your radial vanes. Radial vanes with beta 2 equals to 0. Okay. So this is specific heat at constant pressure. Then this will basically be used in your pressure rise. So if you want to calculate pressure rise across your centrifugal compressor, basically what we are doing, we are pressurizing the air that is coming inside of your centrifugal compressor, and later that will go to your combustion chamber, from combustion chamber to your turbine to your nozzle. Okay, so this is coming from inlet of the gas turbine engine, your centrifugal compressor, from your inlet of gas turbine to your centrifugal compressor. Now we want to increase its pressure. right? Which will increase the efficiency of your combustion. That is why we are basically compressing air. So this can be calculated using this isentropic equation or relation, isentropic relation. This one. Okay. And then we also know that NC or efficiency, isentropic efficiency of your compressor is this, right? So this basically is the work input that you ideally would have given to compressor, and in reality that you need to give is in your denominator. Okay. From here, what you can get is T03 by T01 you can get, and which basically is 1 plus eta C by T01. T03 minus T01. You have this. Okay, so T03 minus T01 is your delta T of stage. So we have expression for this delta T0 for stage. We have expression for this. Okay. And now if you place these two things, first is this, second is this. In this, if you place in this, this is 2, let's say this is 3. So if you place 1 and 3 in 2, then you get P03 by P01, which will come out to be gamma by gamma minus 1. And if you place the values here, from 1, so this will come out to be this. So this basically is your pressure rise across your centrifugal compressor. Okay. Then what is stage efficiency? Stage efficiency is ideally that work that would have been done on the compressor isentropically, and then in reality what we do. So this is this. Okay. So there is an expression for this also, which is something like this. So it is not that difficult to work out. 1 or 2 steps that will do. And in case you are facing some difficulty, you can refer to lecture number 37, or you can just ask me in the comment section. Okay. So this is your stage efficiency. Then degree of reaction. degree of reaction we denote by lambda, which basically is the enthalpy change at your impeller to the enthalpy change at your whole stage. So your stage includes your diffuser also. Okay. And the expression for it is 1 minus half of PW2 by U2, or or this is 1 minus half of phi 2 cot alpha 2. So these are two expressions for your degree of reaction. Phi is your flow coefficient, which is CR2 by U2, and alpha is your fluid angle, okay, between your absolute and your U, C and U, C2 and U. So this is about your lecture number 27 for your centrifugal compressors. The main thing in centrifugal compressors is that you are able to visualize the flows. If you are able to visualize the flows, that is the main thing. Other things you can do on your own, the mathematics you can do. But if you are not able to visualize it correctly, then it's a problem. Okay. So this is about your centrifugal compressor. So we are at question number 5. So we have discussed lecture number 27, and question number 5 we have in front of us, and it says that choose the correct expression for your degree of reaction of the centrifugal compressor. So 4 options have been given to us. Change in the enthalpy ratios have been given, and first one is change in enthalpy of your impeller, and this is in denominator is total enthalpy of the stage. Here is total enthalpy of the impeller, total enthalpy of the stage. This is total enthalpy of the impeller, enthalpy of the stage. This is enthalpy of the impeller and diffuser, and change in total enthalpy through the stage. If you see this degree of reaction, so this is change in enthalpy of impeller to this total enthalpy change in your stage. So in that case, your A option comes out to be the correct one. So your option number A comes out to be the correct one. Okay. Then is your next question, which says that in case of a centrifugal compressor, the square of blade velocity for radial vanes is equal to blade velocity for your radial vanes when your beta 2 is 90 degree. So this is minus phi 2 cot beta 2. Yes. So this is, yeah. So beta, this will come out to be 0, and then This is U2 square, and this is expression for your work done on centrifugal compressor. Okay, so B is the correct option in that case. This was question number 6. Then we have question number 7 to 11. So first of all, we'll have a look at what is given to us, and then we will move on to questions based on this. Please have a look at this paragraph, then we'll move on to questions. So the paragraph says that the impeller of a centrifugal compressor rotates at 18,500 rotations per minute. The compressor delivers the air at volume flow rate of 19.5 meter cube per second with pressure ratio of 5.8 ratio 1. The isentropic efficiency of the compressor is 88%. The axial velocity of the flow is 88 meter per second and is constant throughout. Okay. Then outer uh, radius of the impeller, which has radial blades, is twice the inner one, and neglect the slip coefficient. So sigma you have to neglect. This you have to neglect. And assume the ambient air conditions as this and this 1 bar and 298 Kelvin. Then first is power required to drive the compressor. So we'll first write down what is given to us. So question number 7 to 11. So this is 18,500 RPM. Rotational speed, volume flow rate is 19.5 meter cube per second. Then pressure ratio is 5.8. Then isentropic efficiency of compressor is 0.88. Then temperature, initial temperature is 298 Kelvin. Initial pressure is 1 bar. Then axial velocity is 88 meter per second. Okay. So you know 1, 2, 2 is impeller, 2, 2, 3 is diffuser. Okay. Then question number 7. For question number 7, we need power. Okay. We can calculate this from, it is this basically, but this is this also. Okay. Per second if we see, so this will come out to be in watts. Then this is for here, this is 1.005 kilojoule per kg Kelvin into your T naught 3 minus T naught 1. Okay. Then we have T naught 1, but do we have T naught 3? To find T naught 3, this we have. To find T naught 3, what we will do? We will use this. From here, you can get T naught 3. We have this here, this, and this also. But do we have this? Do we have this? No. But we can calculate it using isentropic relation. This whole ratio is RP basically. Implies T naught 3 dash becomes T naught 1 RP gamma minus 1 by gamma. So T naught is 298, this is 5.8, this is, if we take this gamma as 1.4, so this comes out to be this. Now if we calculate this, this will come out to be around 492.42 Kelvin. So plus T naught 3 dash is, we can use this T naught 3 dash where? Here. So T naught 3 becomes 298 plus 492.42 minus 298 divided by, for your compressor, the isentropic efficiency is this. Now if you calculate this, this will come out to be 518.93 Kelvin. Implies T naught 3. So T naught 3 is this. Now why we are calculating T naught 3? Because we want this work done or power or rate of work done basically. So, so for WC equals to U2 square, this is 1.005 into 518.93 minus 298. So this has been taken for unit mass per rate, I believe. Okay. So if you work this out, this will come out to be 222.03 kilowatt. Okay. U2 square. So this is the answer to your this question. Then to your question number 8. Blade speed at the impeller exit. So blade speed is your U2. So question number 8 solution. So U2 is under root of 2 to 2.03 into 10 raised to power 3. Now if you work this out, this will come out to be 471.20 meter per second. Units you can see, you can handle units, okay. So velocity will come out to be this. Right? So this is your question number 8. Then comes your next question, question number 9. So inlet and outlet diameters of the impeller are. Inlet and outlet diameters you want to know. So first of all, we know D1 is D2 by 2. Now we need to find out D2. Okay. So how do we find out? We will use this expression for U2. For D2, we can use this. So 2 pi r circumference, right? Or pi d. Pi into D2 into number of rotations n divided by 60. 60 is for converting your minutes to seconds. So this is it. Okay. Implies your D2 becomes U2 into 60 divided by pi into n. So U2 is 471.20 into 60 divided by pi into 18500. How much is not required here? So if we calculate this, this will come out to be 0.48 meter. And in that case, hence D1 will come out to be 0.24 meter. Okay. So this is answer to your question number 9, which is 0.48 and 0.24. So your inlet and outlet diameters. Then question number 10 is there, width of the rotor blade at the inlet. Okay. So width of the rotor blade at the inlet. So question number 10. So for this we have this formula. So this is volume flow rate is equal to area into axial velocity. Okay. So this we have 19.5 Okay, then area into axial velocity is 88. Now to find the area, area is this seems to be the area of your surface area of your cylinder. Okay, so because this is 2 pi r and then this is something like length w root, okay, into 88, then 19.5 pi into 0.24 w root we need to find out, or at inlet width, and this will come out to be 19.5 by pi into 0.24 into 88. If you calculate this, this will come out to be 0.29 meters. Okay. So this is it. For question number 10. Then for question number 11, you have impeller and diffuser blade angles in degree, R dash and dash respectively. So question number 11, solution. So alpha root is tan inverse of CA by U1, and alpha tip is tan inverse of CA by U2. U2 we have calculated, CA we have, U1 we have not calculated. So U1 is equal to 2 pi r or pi d1 into number of rotations by 60. So this will be 0.24 into 18500 divided by 60, and this will come out to be 232.47 meter per second. This will come out to be this. Okay, so alpha root becomes tan inverse of 88 by 232.47, which is 20.73 degrees. Alpha tip is tan inverse of 88 by 471.20, which will come out to be 10.57 degrees. So this much. So this is it about questions for lecture number 27, and now we have come to the end of this session. In that case, I'll just conclude this session. So there were 3 lectures in total, 26, lecture number 26 to 28. In lecture number 26, so this whole week was on centrifugal compressors, and in your lecture number 26, we discussed majorly velocity diagrams. What are the forward and backward vanes in a centrifugal compressor and how they affect the pressure coefficient with respect to your flow coefficient. Then expression for your work done was there, which for your radial vanes at the exit comes out to be square of your blade velocity at exit. Then there were other terms like slip factor. What is slip factor? Okay. And then we saw four questions based on that. Then after that, we moved on to lecture number 27, which again was on centrifugal compression. But then here we saw the expression for pressure rise, P03 by P01. Then what is stage efficiency for your centrifugal compressor, and then an expression for that. And then what is the degree of reaction of a centrifugal compressor, which basically is the enthalpy change across the impeller to the total enthalpy change across the stage. So after that, in this, we saw questions. Two, uh, four questions we saw that were numerical type, and then two normal questions we saw. And this way we have conducted this session. So next session again will be on coming Tuesday from 6 to 8 p.m. Till then, goodbye and thanks for watching.